this is a canvas for uh, our lab, and I already talked to you guys about the different parts, but if you go to the data and observation, okay, you're going to see that I talked to you guys. These are the videos that you guys are going to watch and then do snapshots. So you can complete your notebook as if you were doing it. Remember that even though these are recorded, you need to be in the frame of mind that you're actually in the lab and this is what you are seeing. So make notes of the observation. For those of you who did the activity 4, okay, that's being introduced to vernier. A lot of you didn't write your observations. Big part of lab is to write down observations, and albeit you're not in lab to do it, there is still a video there that you need to pick to take a note at and write the observations based on the video. And in fact, it's much more convenient because you can speed it up or slow it down. So if you don't have that down, if you don't write down any of your observations, that's I'm going to have to penalize you, because part of being a scientist is to write objective observations. Okay, so make sure that you guys watch the video and write objective observations of what's going on. Then the data that is collected is here, Excel or the PDF. You probably want the Excel file and you want to download it. So don't click on the preview, because the preview won't allow you to download it. You need to click on the Excel file here, and then your computer will prompt you to save it in your computer, and you need to download that Excel file. The other thing you can do is you can actually go here and download the original Logger Pro data. And when you do that, you will get a zip file. Okay, this is it right here. This is the zip file. It's crystal violet kinetics. And this is it right here. So if you open up these and you need the Logger Pro program, so I give you the link for the Logger Pro program, and you can just get it should be free, okay? So you can put it either in your PC or your Mac. Just click on that and it'll take you to this site. And you want to download Logger Pro right here, okay? If there is information about we are at Miramar and it might ask for a password, but I don't know. But you might also want to do the demo or the Logger Pro Lite, because these are free. You don't need a user for that. But if it does ask you for a user, then just register and tell them that you are from Miramar College. Okay, and then you can do the download. Anyway, when you get the download, let me just show you what it looks like. It's going to look like this. And this is basically the spectrum of the crystal violet. Now, if you want to see the simulation of this, if you are in Logger Pro, then simply go to analysis and then do a replay. Okay, if you do a replay, then it will actually simulate this particular experiment for you. Let me just make sure that I have that. It'll give you this control, and you don't really want to go in real time. You probably want to accelerate this. So I'm going to go about 30 times the original speed, and then I'll just click on start. And when I do that, oops, that's run 1. You got to go over here and do run 1, because if you look at the original data right here, what you will see is that there are no latest run. There's only run 1. So you can just click on these handles and expand it. And so I'm going to do run 1, and I'm going to click on start. And you can see that the data is being filled, and this is the absorption spectra for crystal violet. The important thing about this spectrum is that if you click on the maximum, what you will see is that that corresponds to about 588 nanometers. I'm going to stop this after this second run. It goes on repeat. Okay, so this right here is about 588, and that's what the computer um, looks at when it's doing the experiment, as it's monitoring the methyl reaction. It's setting it up for about 588 nanometers, the maximum, because that's the most sensitive uh, wavelength in terms of monitoring this reaction. So if you open up the this file right here, that's the spectrum. This right here, let's do the room temperature. If I open that up, don't save. What you get is the original data that is in the video. And what I have here is run 1. That was my first run 2, and then the latest run, which is run 3. And what I can do is I can simulate this, and I'm just going to do, say, run 1, and then I'm going to show that. I'm going to stop. The other thing I can do using Logger Pro is I can hide these by right-clicking. I can delete or hide. Okay, so I'm just going to go to data set, and I'm going to hide these things. Data set, hide data set. I'm going to hide data set 2, and I'm going to hide data set latest. And now all I have is run 1. So let's do this. And this is what I actually show in the movie. Okay, I just basically have the computer record this, and that's what you guys see in the movie. I can also do this, hide or show data set 2, show data set 2. Okay, and then I'm going to hide data set 1. And then I'm going to run data set 2. And that's what I have. And this is the data set right here that is in that Excel file right here in Canvas Excel file. Okay. What you can do as well, you might want to do this. Let me show all the data set. I can do that by just closing this and not. Let me go ahead and show all data set latest and run 1. I can click up here, right click, sorry, highlight these, and actually I don't even have to do that. I can just export the data as a CSV, comma, delimited file. And so when I do that, I need to put it in my computer somewhere, and I'm just going to write this as temp. And if I go to that folder where I told the computer to save it, and I open this temp, I'm going to open it with Excel. You can see that it pretty much, here it is in my other screen, downloaded the data, the latest, run 2. This is the latest, run 2 and run 1. And what I can do is I can show this by changing the format in Excel. The alignment should be wrapped. Now I have the labels shown. Okay, so that's how I generated this particular Excel file right here from Logger Pro. I just told Logger Pro to Excel to export the data as a CSV file. I opened it up in Excel and then I renamed it. You got to rename these when you save it. Open it up as a CSV because that's how Logger Pro export files to Excel, and then just save it as an XLSX, which means that that file now is a, let me show you, is an Excel file. The computers recognize what applications to use by the extension of that file name. So CSV is universal. Any spreadsheet program might be able to open that. So if you got Google spreadsheet, you might be able to open that here. If you have Excel, you'll be able to open that, but then save it as an Excel file. That way you don't have to, it'll recognize it automatically. Okay, so this right here is, again, the same as the CSV, but now it's in the correct format for Excel. Okay, so again, just so you know, if you download Logger Pro raw data, then you get the raw data for Logger Pro from Logger Pro, and that's going to be shown, you see, right here. These are the files. Each one of these folders contain the high temperature, and I've separated it so that you have only one of the three trials. This would be trial 1 at high temperature. This would be trial 2 at high temperature, and this would be trial 3 at high temperature. So what I did was I basically took the original file, which was this, deleted the 2 columns, and then resaved it. That's how I generated these graphs right here. You notice that the temperature is actually not constant, unlike what you saw over here. Show you that.
Professor?
Yes.
Not to sidetrack, the CVLT, CVHT, that's low temperature, high temperature, and the CVRT is the first temperature, the room temperature?
CVRT is room temperature, right?
Okay.
And LT is low temperature, and HT is high temperature, right? And if you look at the original Excel file, I actually show you. Let me open up that original Excel file real quick. At the very bottom of each one of those graphs, here's some of the work that I've been doing in preparation of this discussion. You can see the temperature and the average temperature. So if you look at room temperature, there are 2 columns here. It tells you the absorbance and the temperature when that absorbance was measured, and then I just did an average. And so the average temperature as this experiment was running, it actually started at 25.29 and cooled down to 24.69, but the average 25.03. The second trial, it started at 25.1, but ended up at 24.68, and the average was 24.9. So each one of these have a temperature average at the bottom, and but it's still considered for the 3 trials. This would be low temperature, and this would be high temperature for the 3 trials. And you can see that their average in general was higher than the room temperature. So that's what you get from each one of these. This is the original data. These are different Logger Pro for the 3 trials. This is the original data for low temperature. These are the individual Logger Pro for the 3 trials, and so on and so forth. This right here is the spectrum, the original spectrum. So this is the data that you would actually be collecting if you were in lab and doing this experiment. when you zoom in to the temperature, you see that it's really not constant. There's actually a drift, but this is actually good. The fact is the temperature only drifts about 1, maybe 2 degrees. And that's actually good for this lab because throughout the years, it's always been difficult. I mean, seen students have temperature drift as high as 5 degrees. And when that happens, then the rate is constantly changing as your experiment is running because the temperature is changing as well. So as the temperature changes, the rate also changes. So this temperature profile at the top tells you that the drift is not actually that large, and you can take an average. That's the key. Okay, so I'm going to close this right here because those were logger profiles. And let's open up the Excel file. So the Excel file is going to be right here. You download that and it'll look like this. Okay, so let's start with room temperature. Room temperature has 3 trials. Trial 1 is to the far right, trial 2 is the middle, and the latest, which is trial 3, is the far left. This is the kinetics of methylbiologen. The average temperature for the 3 is 24.93. And these are the temperatures down here. So if you take these and you average it over the course of all these trials, the average is 24.93. If you click on this right here, you can see the formula is right here. I add the 3 and divide by 3. Okay. Let me see if I can't blow this up further so that you guys can, it's not so tiny. I think I can blow it up by doing this. Okay. So you guys should be able to see that better. Now, the first thing that you need to do is you need to thin out the data because there's too much data right here. There's way too much data. So the way you thin out the data, let's go back to room temperature, is take a look at, first of all, you want to graph it so you can see what it looks like. Okay. And the way to graph it is first take this tab. These are the different tabs at the bottom. Take this tab and then copy it. And you can do this on the Mac by pressing on Option and then dragging it over. You can just drag it over. And you see how there's a triangle at the bottom? Well, the triangle tells you it's making a copy. So it gives the original file name and then it puts this 2 right next to it. Never mess with the original data. Always make a copy so that if you make a mistake and you need to go back, the original data hasn't been altered. Okay, so I'm just making a copy right here. Then I'm going to thin this out. And the way I thin this out is first I want to graph this. And the way I do that is look up here because you're going to generate the graph of absorbance versus time. So you need to click on the absorbance first, highlight that, and then holding your command button down on your keyboard, you can see that's what I'm pressing. If you look at the my screen, then I select the 2 columns, and then I'm going to tell Excel or whatever program you have, I'm going to do a scattered plot. So this is it right here. And I can certainly change this by double clicking here so that I only see the data from 0 to maybe 350. Okay, so that's what I see right here. And I can certainly change this so that the profile is from like 60 to maybe 20. I click on this. Uh, Axis. Hold on. Select data here. Format axis. So if I do that, I get this menu, and I'm going to change the minimum not to 0. That's what you see right here, 0, but maybe 20.20. And then I'm going to get this to as high as 0.7. That's fine. Hit return, and you can see that's what's happening now. Now, what I need to do is that there's too many data points here. Actually, yeah, there's too many data points. So what I'm going to do is you need about 20 good data set. So I'm just going to take these right here, highlight it to maybe delete every 3, and then just do a universal delete. Then I'm going to take 25 and take it down to about 40 and do a delete. So what I'm doing is, you see how this graph is changing? It's deleting the points in between. The reason why I'm doing that is because, again, there's too many data points, and I don't really need all that data point. So that's what I'm doing right here. I'm thinning it out. I'm thinning out the data. And so eventually it'll look like this. Okay, you get down to 20 data set. And let me just plot this so you guys can see what it looks like. You're thinning out the data set. So now it looks like that. Okay, it's not so continuous. The next thing you want to do after you thin out your data set, and 20 is a good number to thin it out to. So I went from 2 to about 21. So that's 19. That's good enough. Anything above 15, anything below 25 is good enough. Then I went ahead. Let me go ahead and go over here. Actually, let me move over here. And so this is for run 1. I'm going to insert a column. In fact, I'm going to insert 2 columns. After you do this for all 3 trials, you're going to insert 2 columns between the temperature and the absorbance. And the reason why I need to do that is because I'm now going to generate my natural log column and my reciprocal column. So I'm going to put ABS. This is run 1. So I'm just going to relabel this absorption 1 versus just absorption 1. The next one, I'm going to do natural log absorption 1. And the 1 tells you that that's my first run. The 2 here, let me blow that up, tells you that that's my second run right here. And so you just need to make sure that you are clear in your labels. So these are all for the first run. Now, what I'm going to be doing is, you see this column? I gotta generate this column right here. And the way I generate that is I'm going to click on Q2. That's Q2. This is Q and this is 2. So Q2 is equal to, so I'm going to put an equal sign there telling the Excel that that's a function. Natural log is the function name, left parentheses, and then I'm going to click on P2 and see how it fills it in, and then right parentheses and then return. So if I take the natural log of 0.6, it returns a 0.51. I'm next going to highlight 0.51 and then go over to the edge right here. Click down on that and then drag it all the way down. Now I have my absorption column for trial 1. Not absorption, but natural log numbers for trial 1. I'm going to do the same thing for the reciprocal. I'm going to put equals 1 divided by left parentheses, and then I'm going to click on P2, not Q2, but P2. And then right parentheses, and then return. Then I'm going to highlight this right here, and then move my mouse to the right corner, bottom corner, click down on it, and then drag it down. It's my propagation of calculations. Okay. Now I'm ready to plot these. You need to do all of these for trial 1, trial 2, and trial 3. Okay, so let's work trial 1. I'm going to highlight my absorbance, hold my command key down, highlight my run. I also actually need to highlight the heading. Otherwise, I won't get a label. So I'm going to do this again. Highlight my absorbance with the label on top. Hold the command down, highlight the run, and then I could either right-click and say insert a curve, or I can go to the menu and tell Excel to generate a curve, and that's what we have. Okay, that's what we have. And this is basically time at the bottom, absorbance on the left, and that's what you see right there. You can change this so that it goes from like 0.2 to 0.7, and you can truncate this to 350, but I'll leave that for you guys. So that's the first graph. Next, you need to generate a second graph. I'm going to put this at the bottom. And the way you generate the second graph is you highlight natural log absorbance, hold the command button down, and then highlight run. And then again, insert. It's got to be a scattered. Okay, it's got to be a scattered. Right here, scattered. Or you can go in here and say insert scattered, XY scattered. And it generates it for you right there. Okay. So I'm going to size this, and then I'm going to put it down here as well. And notice that the title is based on the axis or the label at the very top. Finally, I'm going to do the third one. I'm going to highlight 1 over absorbance, hold the command button down, highlight time, and then generate a chart, scatter plot right there. So these are the 3 graphs that we are going to analyze. And what we need to do is we need to figure out whether the data is linear for absorbance versus time. It's linear for natural log absorbance versus time, or linear for 1 over absorbance versus time. And how do we do that? We do the linear regression. We click on these right here. Let me go ahead and blow that up so you guys can see. We're not worried about the data points anymore. We're just worried about the graph. And so I'm going to move my mouse and click on one of these dots. And when I do that, it's going to highlight them. But I'm going to right click. And I'm going to, when I do the right click, I'm going to add a trend line. And when I add a trend line, this menu pops up at the right. Let me show you that again. Okay, I'm going to take my data here. I'm going to click on this. I'm going to right click on it, and I'm going to add a trend line. It's going to give me this menu. And then the important part about this menu is that you want to do a linear regression. You want to fit these points to an equation of a line, not exponential, not power polynomial, but linear. You don't want to set the intercept. You don't want the origin to originate 0, 0. Definitely not 0, 0 here. But I do want an equation on the chart and the R squared. R squared will tell you how well these data points fit that line. And right now, you can see that the correlation factor, if you look real closely, let me go ahead and highlight this, right click, make that font larger. So you can see the correlation factor only has 2 nines. You do the same thing for natural log absorbance, okay? Click outside that box, so, and then click one of the data points. It'll highlight the table automatically. You want to right click, and then you want to add a trend line. And when you do that, again, this menu will pop up on the right. You're going to do an equation on the chart and a correlation factor. Don't set it to intercept. If you do the intercept, look what happens to the correlation factor, because it's trying to make the origin 0, 0. That's not the case here. Okay, that's not the case here. So if you take a look at this right here, what you see is that the correlation factor for natural log versus time, let me right click after highlighting that equation and make this 14 so you guys can see. It has 3 nines and a 5. The absorbance versus time has 2 nines and a 3. This is a better fit right here. But we should not ignore the last analysis. That is the one absorbance versus time. Again, right click here, add a trend line, display the equation, do an R squared, and what you see here is that this fit only has 1 9 and an 8. So you can see right away that the best fit in terms of the data fitting a straight line is not absorbance versus time. It's not 1 over absorbance versus time, but it's the natural log of the absorbance versus time. It's a natural log of the absorbance versus time. And what does that tell you? It tells you that if this is the natural log absorbance versus time, then that's a first order reaction. It's first order with respect to the chemical that we are monitoring. And if you take a look at this equation right here, what you will see is that this is the slope, 0.0022. There's a negative here because it's down. But if you take the slope, that's the rate constant. Remember the, let's go back over here. Remember this right here. Let's go back to, I'm going to show you this in the introduction. Right here it tells you natural log absorbance versus time. A linear plot indicates first order kinetics, and K, which is the rate constant, is equal to negative slope. So what you need to do is take that slope, and that's your rate constant, 0.022. So you do that for all 3, okay? And you're going to get an average temperature and an average rate constant for all 3. Now, let's do something for low temperature. Room temperature is pretty easy. The reason why room temperature is pretty easy is because this is a continuous curve. If you plot this right here, then it's just a matter of selecting points. It's just a matter of selecting points, 20 of them. So you have a good representative file. But for low temperature, look what happens when we plot this. Now, be careful of the label, because if you go to the very top and you notice there's practically, if I go all the way to the bottom, there's about 767 data points. That's a lot. You don't need 767. All you need is about 20, 25. Okay? The middle column is temperature. The third column is absorbance. So to thin this out, again, make a copy. Make a copy for the low temperature 2. What you need to do is you need to always select the first one, delete data, so that you're only deleting files that have blank absorbance, but enough of them so that you can thin out the data. So I'm going to delete from here, and suppose I want to keep the data at 10 seconds. Well, there's no absorbance there, so you don't want to select that because that just leaves you a blank. You need to include the 10 seconds run and then delete everything between 0 and 10.24. And I can do that by just deleting that. Okay, then I want to delete, say, 11 all the way to here so that I keep that 23.05. So you're just going to have to do it by inspection. And you need to thin out so you get 20. But let me just graph this for you real quick, because this is a special circumstance where you actually have to pay attention as to the values you're deleting. Okay, so I'm going to highlight this. And again, I'm highlighting the absorbance, not the temperature, but the absorbance. I'm going back down. I'm going to highlight the time. Press the command button down. So, okay, and then I'm just going to go all the way up. Then I'm going to move my mouse over here. So the absorbance and the time are highlighted, release, and then I'm going to do a insert chart, scattered. Now, let me show you the problem with this data set. Problem with this data set is that you can't just randomly start to select so many points from here, because suppose you select a point, say at 100 seconds. 100 seconds is right here. Okay, 100 seconds. Well, the problem of selecting a point at 100 seconds is that you have no real data between this point right here, which is happening at 66.58. If you look at the fine print here, let me zoom in here. So if I select points between 66.58 and 138.27, I'm saving the absorbance here. That's not what I want because there's no real data there. So what I need to do is I need to delete that segment, and you can easily do that by just scrolling down and look at where the absorbance is high and then drops. So I'm going to delete all of this and then probably stop right about, let's see. You gotta be careful because sometimes when you do this, you tend to overextend yourself. Okay, right here to about 340. And then I'm going to go ahead and delete this. Okay, and I want to show you what happens to the graph when I do that. So I'm deleting, well, apparently, let's go back here. Deleting right here. And I'm deleting all the way to right about here. And when I do that, look what happens to the graph. Okay, that should be gone. In fact, I deleted this segment. I'm keeping these. So you need to thin out your data set by keeping points on this curve, 20 of them, and not and ignoring points that are down here. Okay. Um, so that's what you want to do. So when you do that, let me just show you the results of when I do that. It'll look like this. This is the cutout. Okay, I deleted all the points that had no absorbance, and then I thinned it out. So it looks like this. Okay, and then once I thin it out, then I generate my two columns. And you can see that I've generated after absorbance, I put natural log and then 1 over absorbance. Okay, and I'll put this as 3. And the reason why I label this 3 is because this is going to be for trial 3. This is trial 1 at low temperature. In this case, yeah, it's low temperature. This is trial 2 right here for low temperature, and this is trial 3 for low temperature. And I just do the same thing as I did in the previous. Okay, you guys are not doing the experiment, so this is actually a very good tutorial on making sure that you guys know how to use Excel. So let me show you again how that's done. Once you have these, then just type in equals natural log left parentheses, click on the data that you want to do in the natural log, right parentheses, return, click on that cell, drag it down. You've got the, let's do that again. You've now generated the natural log. Same thing here, equals, always start with an equals, 1 divided by left parentheses. In this case, you don't really need a parentheses, but I just do that out of habit. And then propagation of calculations right there. Next thing I want to do is I want to highlight this, hold my command button down, highlight this, and then graph that. Insert a chart, scattered, and that's what you see. Okay, now this particular set has some anomalies. Let's see why it has some anomalies. Okay, and you know it has anomalies because you can see that they've got some points here that shouldn't be there, and you can see that right away when you look at the data. So once you generate a graph, you should be able to see why that didn't. Yeah, this right here is fine. Yeah, I don't know what happened, why it's keeping these data sets right here. Okay, there's ghost information that it seems to be reading. Let me try that again, because that shouldn't happen. Highlight that, and then regenerate the graph, insert, scattered. Okay, that's better. This one was an anomaly. But there's still data points at the end right here. And I see that right here. These data points right here shouldn't be there. So I'm just gonna highlight those and delete it. And I do that by highlighting it and then clear. When I do that, it disappears. Now I can go in and do, you can't have those data points in. Otherwise, when you add a trend line, it's going to try and use those data points in order to fit. And right now, I can see that for this right here, That's not a very good correlation factor. It's not a very good correlation factor. Okay, so you need to do that again for this data set right here. So I'm gonna oops, I'm gonna go back here and remember not, let me just sort of delete those files right there. And graph this versus time. And this is what it'll look. So you guys have the rest of this period all the way through Sunday to do this. Okay, figure out what is the best fit. Remember, for room temperature, you have 3 trials. For low temperature, you have 3 trials. And for high temperature, you have 3 trials. So you have to do this type of analysis for those 9. Okay, you have to do the analysis for those 9. Once you have that, and you've got the rate constant, the slope, based on your analysis, then you can do the Arrhenius equation. So let me show you how that's done. This part is time-based. You're generating absorbance versus time. But once you've done that, you need to get your K's, rate constant, and your temperature. So this is my data for 24.8. This is a different experiment. This is my data for 34.8. That's the temperature. And this is my data for 44.6. So in here, I was able to figure out which of these, absorbance versus time, natural log absorbance versus time, 1 over absorbance versus time, which of these give me the best straight line. And when I do that, say I have this data point right here. Okay, I'm going to graph this, and then I'm going to pull the K out. And the reason why I want to pull the K out is because that's my rate constant. So I'm going to insert or chart, and I'm going to do a correlation factor here, and I'm going to do a trend line. And so when I do that, this particular rate constant is telling me it's 1.0341. Okay, that's the K value. So I'm going to write that K value, and then I'm also going to make a note of that temperature, because the next thing I want to do is I want to generate a graph that looks like this. Hold on. Find that. Here it is. These are the different temperatures. Let me blow this up so that you guys can see. So these are the different temperatures, 24, 34, and 45. Okay. These are the different K values that I got from those data set. These are the temperatures in Kelvin. And the way I do that is I just basically, let me just clear this, write equals 24.4 plus 273.15. I'm just converting them to Kelvin. Okay, I'm converting it to Kelvin. Then I'm taking the reciprocal of that temperature. And the way I do that is I write equals 1 divided by the absolute temperature Then I'm generating the natural log of my rate constant K. So the way I do that is write equals natural log, left parentheses, and then I want to click on K, right parentheses, return. Okay, then this right here is just a regeneration of that. I just copied and paste this over here. And the reason why I did that was because I wanted to highlight this, hold my command button, highlight that, and then generate a graph with 3 points. Okay, then I'm going to add a trend line to that. And when I add a trend line, I'm going to display the equation, display the R factor. It's 0.9161. It's not great, but that's the data that I have, because this intercept right here, that intercept right there, sorry, that slope right there, 0.4819, that slope, well, let's go back to the original discussion here, because I show you here that when you do the Arrhenius equation, right in here, that the slope, the value of EA can be determined from the slope of natural log K rate constant versus 1 over temperature. So this slope of this equation is equal to the activation energy divided by R. So if I multiply 0.4819 by R, 8.314, I now have the activation energy for this reaction, which is what you guys are trying to do for this lab. Okay. So
Excuse
that's
me,
how
Professor.
you do the calculations. Yes.
Just to go over that one more time, we take the m there from log natural of our rate constant over 1 over our temperature in Kelvin, and then you mentioned R. Is that
Yeah.
our correlation factor, or is that
No,
another?
sorry. Yeah, that's always a problem. There's so many variables that's being discussed. Thanks for clarifying that. Let me show you this right here. Let me show you the this PowerPoint, because it's not shown in the equation, but hopefully all of this is going to be, will come together, because you guys have a test on that this weekend. So here is the PowerPoint, and in the PowerPoint, I give you this right here, okay? I also give you, I believe, in the PowerPoint, hold on, towards the end here.
I just commented.
Yeah, I saw that, Sophia. Thanks.
Yeah.
Is that R squared or
No,
just
no, that's
R?
not R squared. That's 8.314. The unit,
Oh,
the
okay.
gas
The
law
ideal
R.
gas constant. Okay,
Yeah,
yeah.
exactly.
From doing the pre-lab, that makes sense. Okay, thank you so
Okay.
much.
Okay.
I was a bit confused because I saw R squared at the bottom. I'm like, wait, where are we pulling R from?
Yeah, the R for, in terms of, here it is. Here it is, this equation right here. You see that? So this is the Arrhenius equation, and the slope M is equal to EA over R, and R is going to be 8.314. Okay, so hopefully that makes sense. So anyway, that's, take a look at this, because this tells you what you need to do in terms of what your write-up is, but that pretty much walks you through, and this is in Zoom, so if you got lost in um, some of my discussion here and what to do, it's summarized in this PowerPoint, but you can also go back to Zoom and take a look at what I did. Eventually, what will happen is you guys are going to generate, figure out, first of all, is the reaction 0th order, 1st order, or 2nd order. And remember that if you establish that it's 2nd order for room temperature, low temperature and high temperature is not going to change the order. It's only going to change the K value. It also better be 2nd order for the low temperature and 2nd order for the high temperature. Don't say that at low temperature it's 1 order, and then at high temperature it's a different, because that doesn't make sense. The mechanism will always be the same. It's just that the rate is going to be different at the different temperature. Once you figure out what order it is because it fits a straight line, then pull the slope from that, and that'll be your rate constant for that temperature. Now you take the rate constant from that temperature and you put it in a table as well as the temperature right here. Convert the temperature to Kelvin, convert the temperature to 1 over Kelvin, and take the natural log of your rate constant, and then you're plotting natural log versus 1 over T, and the slope in that equation times R is the activation energy. Any questions on that?
That's times R? I know we wrote down the Arrhenius equation earlier. That's times R, or is it over R?
No, EA divided by R equals your slope. So what you need to do is you need to take your slope and multiply it by R so that you get this right here. See? You need to
add it as over R. Thank you.
Yeah, yeah. Okay, and that'll be your activation energy. And then once you get that, then this lab is pretty much done. Make sure you talk about how you need to talk about this equation, the reaction, and how you were able to pull out the different information for the kinetics of this particular experiment. And then there's also talking points in the lab manual. But that's your experiment. That's your experiment.
Okay.
Next week, Monday, we're going to talk about the activity 5. Please take a look at that before you do the tests this weekend for those of you in my lecture. That'll help a lot. And then, so we will talk about that on Monday, and then on Wednesday, we will talk about experiment number 2. And experiment number 2 is actually a pretty easy and fast lab. And I did that particular experiment in like a couple of hours just on Tuesday. So I'll have that video up by this weekend.